Hello everyone, hope you are doing fine. My name is Abdul Rehman, and this presentation is about analytical modeling of multiple access interference in C-V2X Sidelink communications, which is going to publish in IEEE International Medit Conference. These are the titles that I'll cover in the upcoming slides, starting from introduction and with the results followed by conclusion. Here we have a plot related to connected car, connected devices, unit sales by communication technology, starting from 2020 to 2030. And the attentions is related to cellular 5G, non-massive machine-type communication and massive machine-type communication, which has a big difference in this line plot. So the study says 1 out of 4 cars will have 5G connectivity by 2025, and cellular communication is a key enabler in smart cities and intelligent transportation systems. More precisely, 5G ultra-reliable low-latency communication has a crucial role in supporting this cellular vehicle to everything communication. And researchers, vendors, companies like 5G Automotive Association, 3GPP, and IEEE are working together to meet the requirement of latency, reliability, availability, bit and loss rate for this 5G communication. And C-V2X mode for communication is being used. For this scheduling scheme, we are using sensing-based semi-precision scheduling in this vehicular-to-vehicular communication. But this SPS may fail in providing quality of standards, so we still need to do some work. For this point of view, the researcher Gonzalez Martin, and they have characterized the statically random traffic generation pattern and discussed 4 types of error in this C-V2X communication. And the first one is error due to half duplex transmission, error due to received signal power below sensing power threshold, error due to propagation effects, and error due to packet collisions. Mostly researchers are using simulating tools to evaluate the performance, and others are also using analytical model, but they're using C-V2X Mode 3 communications or IEEE 802.11p modules. So our contribution for this objectives are we're considering vehicle platooning scenario to fulfill the requirement of latency and reliability. We designed an analytical framework to model the performance of C-V2X Sidelink communication, and I'll discuss 3 different cases, starting from number of available resources, number of interfering vehicles, and lastly, distance between transmitter and receiver. I'll come to this in a minute. So we are using Nagakami long normal composite channel and movement matching approximation methods to statistics the SINR values. You can find details in this research article or in these references. And we are trying to approximate the performance in terms of packet success rate. And at the end, we compare those analytical results with the simulation. So the system model look like this. The transmitter, receiver, and other interfering vehicles. And the distance between these communicating vehicles is constant, the platonic scenario. And the master size for this communication can be between 50 to 1200 bytes, and we're trying to achieve 90% reliability. This is the flow model that are being used for scheduling of resources. We set the time frame TS to sense the resources based on received signal strength index, and then from those available resources we select potential resources based on some properties, and 2 of them are those received signal strength index should be lower than the power threshold, and we won't select those resources which are not sensed during this time frame. And at the end, we have best 20% resources, and then we implement the semi-persistent scheduling scheme. After one time frame, so the resources can keep those resources with this pk probability, or they can reselect them with this 1 minus pk probability. Now it's time for results. So we have packet success probability with respect to number of vehicles. We set the number of resources to 8, and we are increasing the number of vehicles from 8 to 16 with 3 different distances between transmitter and receiver, 20, 50, and 100 meter, blue, red, and black respectively. And we can see the efficiency of scheduling scheme is distributing the resources among the vehicles from 8 to 16. In the second plot, we are increasing the number of resources from 7 to 15 and fix the number of interfering vehicles to 15. The probability of successfully receiving a packet is increasing with respect to number of resources as we increase the number of resources. And at the end, when the number of resources reach to 15 and number of vehicles 15, this is the point where each vehicle can get a chance to reserve a dedicated communication slot for each vehicle. In the last result, we fix the number of resources and plot the results of packet success probability versus distance. We have 3 different cases, for number of vehicles equal to 8, 12, and 16. When the number of communicating vehicles is larger than the number of resources, the performance decreases, and the impact of channel sensing failure may affect the performance more significantly compared to increasing the number of vehicles. We can see when there is a less difference when the number of vehicles is equal to 12 and 16, and a big difference when the number of vehicles is equal to 8. To summarize this presentation, we propose an analytical model to estimate the performance of C-V2X Sidelink communication. We use the moment matching approximation for the statistics of the SINR values and then compare those values with the block error rate. We have a vehicle platooning scenario based on available resources, number of interfering vehicles, and distance between transmitter and receiver. From the results, the model is proven, and it can be used for Sidelink communication. For the future work, we are planning to use OpenCV2X as a simulator for the validation of this proposed analytical model. You can discuss this research item for this presentation for detail, and if you still have questions, I will be happy to answer you. Please write me down. Thank you for your time.